with that, let's get started. We will be reverting to version 1 of this notebook, ATE versus difference in means. I just want to reiterate this concept with a simple example. All right, so in order to measure the average treatment effect, we are given the following data frame. You have 5 IDs, you have 5 individuals. T equals 1 for 3 of these individuals. This means कि ये वो individuals हैं that were assigned to the treatment group where the treatment was administered. And then there are 2 individuals for which T equals 0. These individuals were assigned to the control group. Then you have the outcome given that the treatment was administered and the outcome without the treatment. All right, so this is yi1 and yi0. I will first of all try and find the individual treatment effect. So for each individual, this is fairly straightforward. I will do yi1 minus yi0 for every individual. In pandas, we know that this is really straightforward. You just declare a new column, उसका आप name specify करते हैं, and then you equate it to, well, whatever operation you're performing between these two. So this is what that looks like. Individual causal effect equals DF outcome with treatment minus DF outcome without treatment. After which, this is what our data frame looks like. What I will do now is I will just find the average of these individual causal effects. Hence, I get the average treatment effect, which in this case is equal to 0.14. ठीक है, इसकी positive value है. Maybe it tells me that my treatment has been beneficial for these people. Okay, now the problem is, although in the real world, you can only have one of these two for an individual. Because the thing is, if an individual was given a treatment, तो आप measure कर सकते हैं only the outcome with the treatment. This is a counterfactual. You cannot measure the outcome without the treatment. This is what would have happened if the individual was not given the treatment. So in the real world, you actually have only 0.8 against this individual, 0.7 here, 0.5 here. And similarly, 0k against you only have this value, 0.7 here and 0.9 here. Because if this individual was not given the treatment, तो आप सिर्फ measure कर सकते हैं their outcome without the treatment. This would be their potential outcome with the treatment. In actual, you cannot really measure that. And this is where difference in means comes in. Difference in means is it's an estimator for the average treatment effect. However, we've studied that the difference in means is not always equal to the average treatment effect. But let's look at this scenario. अगर हमने difference in means find करना हो, तो how would we do that? So what I will do is I will select all the individuals that were given the treatment and I will find the average of their outcome with the treatment because this can be measured. Similarly, I will filter out all the individuals that were not given the treatment and I already have the value of their outcome without treatment. So मैं इनकी average ले लूंगी. When I subtract the second average from the first, I will get my difference in means. So let's try and do that. This is fairly straightforward, but really I definitely do want to show you guys how I have split my data frame. So I have a treatment group now. That's my treatment group. And then I have a control group. So this is what I did. अब treatment group में मैं ये वाली values measure कर सकती हूँ. Control group में I'm measuring these two values. So now I can just find the means and then subtract them. So this is essentially what we are doing over here. So I find the treatment mean. जब मैंने filter कर लिया, so for the treatment group, it is the outcome with treatment dot mean. Similarly, I find the mean for the control group, the outcome without treatment dot mean. And then I calculate the difference in means. And this is quite interesting actually. My average treatment effect was 0.14, which kind of told me that my treatment is beneficial. It has a positive impact on the outcome. But my difference in means is negative 0.13, which kind of tells me that if you give the treatment to an individual, तो उनका जो outcome है, it is not beneficial for them. It has an adverse effect, which probably is not going to be true because we have our exact value of ATE over here with us as well. So the thing is though, ATE is typically not equal to difference in means. This happens because of confounding variables, a lot of which go unobserved. And the thing is, we are trying to, well, in a randomized control trial, you put individuals in the treatment and the control group at absolutely random. So if I were to take a few individuals out of the treatment group and swap them with a few individuals of the control group, so ideally in an RCT, now what's going to happen is it will have no impact whatsoever. But in a real world and in an observational study where you are already given data, so you don't know कि उस data का origin क्या था, and there could be confounding factors involved. When there are no confounding factors involved, when there was randomness in assignment, then the difference in means is going to be equal to the average treatment effect. All right, with that, we are going to move on to version 2 of our notebook. And version 2 includes a practice question on conditional probability. I believe that, yeah, inshallah, we will include one in ungraded homework 4 as well. And I will highly encourage you to attempt these questions before your upcoming midterm exam. In fact, even for those of you listening, once we go over this, so before we solve our probability problem, just pause and try to attempt it on your own. You will benefit from it. Then, if you're unable to, just go ahead and tally your solution. All right, let's look at this scenario. Consider a doctor who administers two different treatments for patients with kidney stones, depending on the size of stones. Treatment A is surgical, and then treatment B is simple pills. So, naturally, your doctor prefers surgeries for people with more severe cases and larger stones, um, and well, pills otherwise. The following are the success rates of her treatment after a year. So, let's see what happens here. You have treatment A, treatment B for small stones, large stones, and then you have combined results. जो आपको percentages दी हुई हैं, that's the percentage of people that recovered in each group. That is the success rate of the treatment, as you can say. So, in essentially, I had 87 individuals with small stones who were given treatment A. 84 of whom recovered, which means that there is a 96% success rate for treatment A on individuals with small stones. Similarly, you can interpret the rest as well. So, the first question is if a new patient comes in with kidney stones, and suppose this new patient doesn't really know the size of their kidney stones, so, should your doctor recommend treatment A or treatment B just based off of this data? अब हमें stones का size नहीं पता. I will encourage you to pause and think. So, what I observe over here is that individually treatment A performs better than treatment B on small stones. On small stones, treatment A का success rate 96% है, and then treatment B का success rate is 87%. Similarly, treatment A outperforms treatment B for large stones as well. So treatment A का large stones पे 73% success rate है, and treatment B का large stones पे 68% success rate है. So this is one possible way of approaching my problem. I can say that the doctor should administer treatment A because treatment A works better than treatment B for both large stones and small stones. या उसका success rate ज़्यादा अच्छा है. Alternatively, when you combine these results for both kinds of stones, you observe that now treatment B has a success rate of 82%, while treatment A has a success rate of, well, 79%. So you could also say that the doctor should recommend treatment B because overall it performs better. Overall, it has a better rate of success. So how did I compute these percentages? Just to tell you quickly, I had 87. Oh, my bad. 87 plus 263. These were the total number of people who were given treatment A. And then 84 plus 192. These were the total number of people for which treatment A was successful. And similarly, I computed this for treatment B as well. This is fairly paradoxical though, and I will help you all recall that this is the Simpson's paradox. Simpson's paradox में what we observe is कि जो individually हमें across groups rates नजर आ रहे होते हैं या probabilities, um, they flip once we merge groups together. So या तो ये पहले ज्यादा हो सकता था बाद में कम हो जाता and or like vice versa. That's the Simpson's paradox. Uh, why does it happen though? This we will explore in our very next notebook. We will go over another example. So let's not go there right now. Rather, let's figure out how we are going to. So, do you see any contradictions in the data? You can go through this on your own. Right now, what we are gonna do is अच्छा एक certain depth तक हम यहाँ पे भी इसको देख लेते हैं. Let's make a causal directed acyclic graph for this problem. If you would like, you can pause over here and try and construct this graph yourself as well. So I have three things in my graph: treatment, size of stones, and recovery rate. This is what my graph comes out to be. Of course, the treatment is going to impact the recovery, but size impacts treatment and size impacts recovery as well. So now let's recall that this particular structure that we observe in a causal DAG is called a confounder. Size is a confounding variable. A confounding variable is something that affects both your treatment and your outcome directly or through another variable. So size एक confounder है. जब ऐसा होता है, तो the problem essentially is कि when I'm trying to measure the effect of treatment on recovery, I am not really able to isolate the effect of treatment on recovery just by looking at my data. Because if I observe recovery, I cannot be certain कि recovery सिर्फ treatment की वजह से है या size of stones की वजह से थी. To put it even more simply, maybe people with smaller stones are more likely to recover. People with larger stones are more likely to recover. One treatment could definitely be more effective than the other, but maybe I'm just not administering the more effective treatment to a lot of people just based on the size of their stones, which is small. So, anyway, what are we going to do over here? We have to control for size. And how do you control for size? So, in order to find the treatment effect over here, you will have to control for your confounder. This is how I will do it. I will find the probability of recovery given that my treatment is equal to A. And then I will find the probability of recovery given that my treatment equals B. While what am I doing? I'm controlling for size. So this will be equal to the probability of recovery given that the treatment is A and the size is small, multiplied by the probability that the size is small. And then what I will do is कि मैं इसमें लार्ज साइज वाले को भी ऐड कर दूंगी. So this is how I will find the probability for treatment, sorry, the probability of recovery given that the treatment is A, and I am controlling for size. I can do the exact same thing for B as well. This is how I would do so. And it's important to understand over here, कि इस example में तो you just have one confounding variable. So this is how you went about it. What if you had two confounding variables or multiple confounding variables? So recall from your causal inference lecture and your lecture slides कि आपको हर कोवेरिएट के लिए, सॉरी नॉट कोवेरिएट, हर कंफाउंडर के लिए आपको इसी तरह कंट्रोल करना पड़ता है. So suppose I also had age and age had two possible values, young and old. So this is how I would have to go about it. And then I would have to multiply it with the probability that the age is young, and I would have to make all combinations essentially. So size is small, age is young. Size is large, age is young. Size is small, age is, sorry, size is small, age is old, and size is large, age is old. So ये जहाँ पे two values add हुई हैं वहाँ पे three values add होंगी. Similarly, if I have three confounding variables, then I have to control for all three of them over here. All right, anyway, I am going to leave the solution over here with you guys because now you just have to plug in values. So what I'm gonna do is probability that the treatment is A and the size is small. ये तो मुझे given है. Treatment is A, size is small. Probability of recovery is 96%, 0.96. Then that is multiplied by the probability that the size is small. So what is the probability that the size is small? I have 350 plus 350 stones, 700 stones in total. 87 plus 270 of these stones, ये बनते हैं आपके 357 stones, were small. The rest were large stones. So I have 357 divided by 700. Similarly, you can plug in the rest of the values as well. And for your information, so this is what was given to you in the slides as well, adjusting for covariates. This is how you adjust for covariates. And this is the solution for the problem. So exactly वही math हमने किया. You just have to do it for, you just have to plug in for every single entry over here. And so it comes out that the probability of recovery, given that the treatment A conditioned on size is 85%, and the probability of recovery, given that the treatment is B, conditioned on size is 78%. So now I can confidently say that treatment A overall performs better. With that, let's move on to our Simpson's paradox notebook. So we're going to go over a case study and we're going to understand this better. We're going to ground it with a good example. I don't want you guys to focus on the data generating algorithm right now, but we are using a data generating algorithm in this example. I will definitely circle back to it though. So let's go over what we are doing over here. Let's give you some context. So, suppose this is interesting. The world is confronted with a rare disease for which the world's public health agencies are urgently trying to find therapies or solutions. Scientists have proposed a new drug, but its effectiveness has not fully been demonstrated yet. So, they've introduced a new drug, but they're not sure how effective it is right now. As your government's top data scientist, you have been tasked with finding evidence of the drug's effectiveness. This is not a light task, and your feedback will inform the country's treatment policy. However, there is not enough time to run a clinical study. आप एक trial नहीं run कर सकते. आपके पास instead observational data available है. So let's see. Instead, you have access to data that was collected in a neighboring country which has already started to use the drug on its patients. And the dataset contains the following variables. So what do we have over here? हमारे पास observational data है किसी और country का. These are the variables that are given to us. Z is the severity of symptoms. Z can have only one of these three values, either mild, which is denoted by 0, or strong, which is denoted by 1, or critical, which is denoted by 2. Then I have another variable, A. A just tells you whether the treatment was administered or not. अगर A की value 1 है, it means that the person was given treatment. अगर A की value 0 है, तो the person was not given the treatment. They were in your control group right now. And then I have Y. Y is the survival after 1 month. And Y की सिर्फ दो values हो सकती हैं. Either the person is dead after a month or the person is still alive. Okay, with that, let's get started. I will show you what your data looks like as well. So I have 10,000 rows and 3 columns, Z, A, and Y. Once again, Z is the severity of symptoms, 0, 1, and 2 surface की value होगी where 2 is critical. Then A is whether the treatment was administered or not, and Y just tells you whether the person was alive after 1 month or not. So let's see, this is what you are interested in measuring, the average treatment effect, which means the chances of survival if someone takes the treatment versus the chances of survival if someone does not take the treatment. So अभी हम क्या कर रहे हैं? Like I mentioned, we cannot figure out whether the person was dead or alive if they weren't given the treatment, given that they were given the treatment. Let me elaborate on that. Suppose आपके पास ये individual है on the 0th row. This individual had severe symptoms too. Sorry, critical symptoms. Severe तो one था. And this person was given treatment. So outcome ये था that the person died. The thing is though कि मुझे सिर्फ ये पता है what happened if the person was given the treatment. मुझे नहीं पता what could have happened if the person was not given the treatment. That would be my counterfactual. What would have happened if the treatment was not administered? So I cannot directly just compute the ATE. What I can do is कि मैं find कर सकती हूँ the difference in means, which we just looked at right now as well. So this is the difference in mean. You have the expected value for the treatment, for the recovery for Y, given that the treatment was administered, minus Y, given that the treatment was not administered. And these are the averages that I have been able to compute. So these are what my averages come out to be. When I take a difference of these averages, this is what I get. I get negative 0.11. To clarify, that's not exactly your ATE, that's an estimate of your ATE. Okay, often students confuse these things. You're finding the difference in means, which is giving you an estimate for your ATE. Anyway, when I find my mean over here and I subtract it for the mean from the mean for this group, this is what I get. Negative 0.11. So what do you conclude from this? I want you to quickly pause and think about this here as well. So essentially, this tells us that the treatment has a detrimental effect on the outcome of the individual. मतलब अगर आप treatment administer करेंगे तो you are increasing the likelihood that the patient will die in a month. So this is fairly odd. This not only tells you that the treatment is ineffective, in fact, it tells you that the treatment will make the outcome further worse, which may or may not be true. So, anyway, you start to question these conclusions and you decide to analyze whether the treatment effect varies depending upon the severity of symptoms. अब हम हर symptoms के against देखेंगे. So, what am I doing? I am essentially conditioning right now on my symptoms, and I just want to see, well, I'm not exactly conditioning on it yet. I will do that along the way, lekin I will find the mean for each individual group. Like I want to understand कि जिन patients के symptoms mild थे उन पे क्या effect था इस drug का, जिन patient के symptoms severe थे उन पे what was the rate of recovery, how effective was this drug, and I also want to see how effective this drug was for patients जिनके symptoms severe थे. So this is what I find. Interestingly, all of these values are positive. However, my combined value was negative. So let's see. This is what we see, the conditional average treatment effect by disease severity. And I see positive values for all three symptoms. This is essentially exactly what the Simpson's paradox tells you about. I observe an effect in my data across different classes that completely reverses as soon as I merge all those three classes. That is your Simpson's paradox with a slightly more technical example. So, what do we conclude? So, while the treatment is detrimental overall, it has a positive effect on the survival rate for each individual group. Those with mild, strong, and critical symptoms, they all are recovering. Now we're puzzled and we want to dig deeper. But I quickly want to tell you कि अगर हम इसका construct करें causal directed acyclic graph, we will realize that the severity of symptoms is actually a confounder. But let's hold on to that thought. So now I make another plot for the probability of receiving the treatment with respect to symptoms. And what do I observe over here? A fairly positive trend. People जिनके symptoms ज़्यादा severe हैं are more likely to receive the treatment. So people with critical symptoms are much more likely to receive treatment than people with strong symptoms, which are more likely to receive treatment than people with mild symptoms. So, what do we observe over here? The probability of being treated clearly increases with the strength of the symptoms. That's probably because of some policy that the government had introduced. कि अगर आपके symptoms एक certain amount से ज़्यादा strong हैं, तो they will want to treat the patient for it. So let's look into the relationship between the strength of these symptoms and the probability of survival now. I just want to quickly show you these previous graphs so that you do not mix these up. पहले हमने conditional average treatment effect find किया था by the disease severity. So essentially जो हम difference in means find कर रहे थे, we found exactly that, but we found it for each individual symptom group. After that, we made a drug which showed us the probability of receiving drug with regards to symptoms for each individual symptom class. Now we are looking at the probability of survival with respect to symptoms. So I can also see that as the symptoms become more severe, the probability of survival decreases. So between my three variables, now what have I observed? That, well, this is clear. The probability of survival clearly decreases with the intensity of symptoms. Now I know कि symptoms की intensity जो है वो determine कर रही है whether the people will receive the treatment or not. You know, I can see that from this graph right here. If the symptoms are more severe, then the people are more likely to receive treatment. So the severity of symptoms, which is Z, is impacting whether the treatment is administered or not, which is A. Similarly, Z is also impacting Y, which is survival. However, I am just trying to observe the effect of Y on Z. I am not able to isolate this effect because this is what my causal directed acyclic graph comes out to be. Z is a confounder. In order to isolate the effect of A on Y, I have to be able to control for Z. So this is what the causal directed acyclic graph comes out to be. There are two paths between A and Y. जो पहली वाली path है, that path is transmitting spurious correlations from A till Y. जो A till Y directly path है, that is the only path that will reveal the true total causal effect of A on Y. So what essentially do we do in this scenario? Hmm. I could I could control for Z, and in this scenario where I am not able to control for Z, I want you all to recall that controlling for Z is the exact same as intervening and fixing the value of A. Right now, I have a certain data generating algorithm. That data generating algorithm, which I have not walked you through yet, ensures that Z is causing A in some way and Z is also causing Y in some way. So essentially, जो Z से A तक arrow जा रहा है, if I'm able to get rid of that and just, replace it with a coin flip, then and only then I will be able to determine the true impact of A on Y. So I just want to show you our previous data generating algorithm, a bird's eye view at this point. This is how you are generating data. Now let's look at this. हमने random integer generate किया for Z between 0 and 3. So 0, 1 या 2 सिर्फ generate होगा. This is the number of samples that I'm generating. So clearly nothing else is impacting Z. Z is completely random. And then I have policy. Policy may I am specifying the probability of treatment for each Z. So I want you to really focus on this. 5% chance of receiving the treatment if Z is 0. So 5% chance of receiving the treatment if your symptoms are mild. 50% chance of receiving the treatment if your symptoms are severe. 90% chance of receiving the treatment if your symptoms are critical. And that is how I am generating A के samples. I generate a random probability. ये function आपको 0 से 1 के बीच में value return करता है. And then I check for each Z in Z. Anyway, once you have obtained A के लिए values as well, so now I want to construct Y. Now look at this. Anyway, इस structure को हम change नहीं करेंगे. 75% chance of survival for mild symptoms that were untreated. 25% chance of survival for severe symptoms that were untreated. 10% chance of survival for critical symptoms that were untreated. And similarly, मैंने ये probabilities treated के लिए भी construct कर ली and उसको use करके I generated my data. Hence, my data was systematically generated, and this is what my data generating algorithm translates to in my graph. This is what I want to do. So essentially, now I want to intervene and cut the association between Z and A. If I fix the value of A, I should be able to do that. So what am I gonna do? Actually, I have accidentally revealed the solution altogether. Anyway, to replace this with the coin flip, I want कि एक person को treatment group assign होता है या control group assign होता है. Like उन्हें treatment दिया जाता है या नहीं दिया जाता. This is not determined by symptoms, rather there is an equal chance for each of the three categories. So this is what I did. जो पहले policy ये थी 5%, 50%, 90%. By the way, they do not sum up to 100% because it's not a distribution. All I'm saying is that there is a 5% chance that a person is given a treatment if their symptoms were mild. There's a 95% chance that they were not given the treatment if their symptoms were mild, and so on and so forth. अब इसको मैंने 50-50 से replace कर दिया. So 50% chance of getting the treatment for each kind of symptoms. And so I generate my data again. Now look at my updated graph. Probability of receiving the drug with respect to symptoms, 50% each. And now this is what I will do. I will compute the expected value of Y recovery given that do A equals 1. Matlab, I intervene, I fix the value of A to 1. What would have happened if I would have administered this treatment minus the expected value of recovery Y, given that do A equals 0. I intervene and I give no treatment. So let's see. This is what I observe now. This is interesting because isko use karke, if I again find the difference in means, just by the way, I will emphasize again that we are finding the difference in means right now. If you look at our piece of code as well, तो ये पहले filter out कर लेता है. Just by the way, this is the same thing as writing this down because you're more familiar with that syntax that we've been covering. So anyway, ये filter out कर लेता है treatment true को, treatment false को, and then ये mean values find करता है. So now the difference in means comes out to be 0.276. Now I can see that the drug actually has a positive effect on survival. So people have a better chance of surviving if they are given the drug. To compare, जस्ट यूजिंग कंडीशनल्स, जब हमने सिर्फ कंडीशनल ATE कैलकुलेट किया था, conditional average treatment effect using conditional probabilities, the answer was negative 0.11, which meant that the treatment had an adverse effect on individuals, which was not actually true because I was observing this because I had a confounder, the severity of symptoms. जब मैंने severity of symptoms का link cut कर दिया with treatment assignment and I made the treatment assignment random, then I observed that my average treatment effect is positive. And that means that the treatment is in fact effective. Hence, I want you to understand कि conditional probability से जो result निकलता है, it can be biased. And I want you to pause over here for a second and think about when these two values are going to be equal. It has been tested before and it is a very important concept. When are these two going to be equal then? When is conditioning going to give you the exact same result as randomization, as intervening? So this happens when there are either no confounding variables or all confounding variables have already been controlled for. Just remember the difference between conditioning and acting or intervening as well. Conditioning ke andar, you are just observing the data. So an example is that observing people who drink coffee tend to have higher rates of heart disease. This observation alone doesn't prove that coffee is what's causing heart disease because there could be other factors involved. Let me break it down a little further. This doesn't tell you that people who drink coffee tend to have heart disease. This tells you among people who have heart disease, a lot of them are drinking coffee, are coffee drinkers. So this is just what happens to occur in your data. It just tells you what's already in your data. Acting या intervening में, you can establish causal links because like this is like an RCT. Some people are assigned to drink coffee, some people are assigned to not drink coffee. And then if you compare their heart disease rates, so then you can establish a causal link. Anyway, a few final words. When concluding data analysis, it is important to think about the nature of the data, how it could have been generated. If you fail to do so, like the way that we constructed our causal DAG and we immediately determined कि confounder की वजह से हमारे results biased हैं. So if you fail to do so, you would have concluded that a treatment was ineffective while you have an effective solution to the rare. With that, we're gonna move on to the last notebook that we will be going over in today's session. And this covers multivariate regression, but a lot of you may not remember. This is from lecture 12. इसको एक दफा revisit भी करें. When we were looking at average treatment effect, we saw that difference in means is one way of estimating the average treatment effect. Similarly, you have multivariate regression. For those of you who have already taken ML, you're already familiar with regression as well. For those of you who haven't, do not worry about it because regression हमने इस course में भी cover करनी है in module 4, which we will be starting soon inshallah, and then I'll hold a tutorial to go over that in code as well. Anyway, what do? In regression analysis, you build a model of y, where y is your outcome, as a function of all the covariates x and the treatment t. So I want to tell you कि covariates exactly क्या है. Covariates are variables, not always confounders, by the way. They are just other variables which are involved in your data generating algorithm, in your causal graph, but these are variables that we are not interested in. We are interested in the treatment and the impact that the treatment has on the outcome. But when we try and fit a model for y and then we add all the covariates to that model and then we also add the treatment to that model, for instance, आपके पास cholesterol था, you were trying to determine whether exercise is what is impacting cholesterol or not. And then you had a covariate age, which was affecting cholesterol, maybe exercise was affecting it, it was affecting exercise. So आपने equation बना ली, you formed a regression equation for this. If you have other variables, you would just add them to this equation. Then when you adjust your model, you fit your model to your data, it will help you estimate. It will essentially help you uh, incorporate all of your other covariates and it will help you estimate the treatment effect. Let's look at this through an example. Unless you see an example, it's hard to be clear about this. So this is a case study borrowed from borrowed from Dr. Hassan's offering. What are we looking at? A paradoxical collider effect. Collider effect पे हम बाद में आते हैं. I will help you all recall what that is. The problem at hand is, what is the causal effect of sodium intake on blood pressure? You are looking at good controls and you're looking at bad controls. We don't know which is which right now, but you are trying to determine the causal effect of sodium intake on blood pressure. So इसके लिए आपके पास ये research paper का link है जहाँ से data borrow किया हुआ है. For those of you interested, you're welcome to explore this on your own. Let's go over the problem statement. In Southeast Asia, we often consume food with high salt content. Food with high salt content is going to impact blood pressure. The National Health Survey of Pakistan estimated that hypertension, which is, well, high blood pressure, affects 18% of Pakistani adults. It is well known that high blood pressure is associated with an increased risk of mortality, increased risk of death. So, we are interested in finding the causal effect of sodium intake on blood pressure. Our data is coming from this paper. The outcome variable y is the systolic blood pressure. This is a continuous variable. Then the treatment is sodium intake. Sodium intake is a binary variable. क्योंकि हमने अपने data के अंदर one store किया है if the sodium intake was more than 3.5 milligrams and zero otherwise. So, either high sodium intake or low sodium intake, either 0 or 1. The measured covariates that are denoted by X, there are two covariates over here. We're not commenting on the nature of these covariates. We just know that there are two covariates right now. So you have the age and the amount of protein in the urine of an individual. We have data on 1 million individuals. In this example, you already know that suppose you know okay, the true average treatment effect is equal to 1.05. Let's see. So let's look at our data set. This is what it looks like. 1 million rows, 4 variables recorded: blood pressure, sodium, age, and protein and urea. I will give you guys a few seconds to look at this data set and then we'll move on. All right, moving on with our data set. So what do I do? In order to, now I'm going to try and find the difference in means, which as we know is an estimate of average treatment effect. In this example, I'm already telling you कि जो आपका वैसे average treatment effect है, that is equal to 1.05. Now I will find the difference in means, and we already know how we're going to do that. I will create two new data frames, two groups, one where sodium equals 1, the other where sodium equals 0. And दोनों groups में I will compute the mean blood pressure and then take their difference. So this is what it comes out to be. 133 for the group with high salt consumption, 127 for the control group. So when I take the difference, my ATE comes out to be 5.32, but this is a large overestimate of my actual ATE. Ultimately, it means that there's some confounder involved, but we're gonna look at that later. So exactly वही चीज है जो plot की हुई है यहाँ पे. Anyway, moving on towards your multivariate regression design, you're gonna try and estimate the ATE by controlling for different variables. And you're controlling for what variables? जो आप add कर रहे हैं as covariates in your regression model. So y equals alpha 0 plus alpha 1 into sodium plus epsilon is a small value that goes into your regression model. This is your intercept and this is your slope for sodium. So abhi I'm actually only considering two things, the treatment and the outcome, sodium and blood pressure. I'm not considering age and I'm not considering protein and urea. तो मैंने कोई भी covariates नहीं consider किए. You do not need to fixate on the code a lot, but I want to walk you through what's happening over here. हमने अपना डेटा फ्रेम लिया, उसमें से सिर्फ सोडियम को filter out कर लिया as x, since no controls were added. So x is whatever is going on this side, and then y is the outcome. Y के अंदर you only stored the blood pressure. Then I instantiate a model, linear regression. I fit the model using x and y. I copy my data frame, and now against my data frame, मैं सिर्फ सोडियम को use कर रही हूँ to predict for what I am doing over here. जब मेरा model हो गया fit, after that I create two copies of my data frame. एक कॉपी के अंदर I set all the sodium values to 1. दूसरी कॉपी के अंदर I set all of the sodium values to 0. And now I try and determine कि जिसमें मैंने sodium value को 1 set किया था for every single individual. I'm doing this for every single individual, even though in actual, and that was the limitation with the difference in means approach as well, कि मेरे पास सब individuals का data counterfactuals का नहीं था. If an individual was consuming sodium, I had no idea to determine, I had no way of determining what would have happened if that same person had not consumed sodium. मुझे सिर्फ ये पता है कि क्या हुआ जब उस person ने sodium consume किया, what was their blood pressure, what was their outcome. This is where multivariate regression is helping you. I have a model जिसको मैं सारे पेशेंट्स की सोडियम वैल्यू ट्रीटमेंट वैल्यू 1 करके दे दूंगी और वो उन सब के लिए आउटकम प्रेडिक्ट करेगा. सो नाउ आई हैव ऑल द आउटकम्स इफ द ट्रीटमेंट वाज 1. आई विल डू द सेम थिंग बाय सेटिंग द ट्रीटमेंट टू 0 एज वेल एंड देन द मॉडल विल प्रिडिक्ट एंड टेल मी कि अगर वैल्यू 0 थी तो उन सब पेशेंट्स का क्या क्या आउटकम होगा. व्हेन आई टेक देयर डिफरेंस तो इट हेल्प्स मी find a better estimate of my average treatment effect. Without right now controlling for anything, this comes out to be 5.32, which is essentially fairly similar to difference in means. But to be fair, the idea is to be able to include covariates, and abhi humne koi bhi covariate nahi include kiya. Then suppose that I include age with sodium as well. So everything else remains the same except कि जहाँ पे मैंने sodium रखा था xt में वहाँ पे I'm including sodium comma age. I'm including both of them. Then I do the exact same thing and my ATE estimate comes out to be 1.045, which is fairly close to the average ATE, which means कि मुझे फायदा हुआ है एक कोवेरिएट को include करने का. Now I will try, and I will actually comment on this later. Now I will try and include my other covariate as well. अब मेरे पास sodium है, which is a treatment. I have age, which is a covariate, and I have protein and urea, which is also a covariate. So just this thing changes, everything else remains the same, and the ATE with adjustment comes out to be a big underestimate of what I was actually trying to find. Now it's 0.848. इससे पहले this was still closer to my actual answer. यहाँ पे it was a big overestimate of my actual answer. So why are we observing this? Now I will comment on the nature of these covariates. I have sodium intake and where is this? Yeah, here we go. मेरे पास sodium intake है, which is impacting blood pressure. I have age. Age is a confounder. Age is impacting my sodium intake, perhaps, and then age is impacting the blood pressure. With age, people are more likely to have high blood pressure. This is just based off of our data. I'm not telling you that older people are likely to consume more sodium or younger people are likely to consume more sodium. हमें ये नहीं पता. This is off of the data that was already provided to us. Age is a confounder. So जब मैंने age को अपने regression model के अंदर डाल दिया, तो उससे ये हुआ कि age was automatically adjusted for. It was important to adjust for age, which is why my outcome जो आया, it was no longer an overestimate of the actual average treatment effect. On the other hand, if a person is consuming more sodium, they are likely to have more protein in their urine. ये भी एक association है. And then in fact, it's a fairly causal association. On the other hand, if a person has high blood pressure, they are also more likely to have protein in their urea. So the problem with this is that now protein is actually acting as a collider. Both my treatment and my outcome have a common effect, which is protein in urine. And this is my problem. जो आपके पास colliders होते हैं, you do not control for colliders because when you do control for colliders, you introduce a collider bias. So जब मैंने अपनी regression equation के अंदर collider को भी डाल दिया, so now my result was an underestimate. Alright, that will be all from my side. If you guys have any questions about this tutorial, please do reach out to me. Thank you.